emitter amplifier. Unbeknownst to you, we've already taken a look at the common emitter, so we'll be revisiting an old circuit in a new light. This familiar circuit in the upper left is the first amplifier we're going to study, but now we're going to refer to it as a common emitter amplifier. It has that name because the emitter is grounded. It's the same circuit that we studied when we were calculating large signal bias points for BJT circuits, but I've added a small signal input source with a source resistance Rs that's connected to the base through a capacitor. I've also added a load RL that's connected to the collector through a capacitor. Connecting a series capacitor to a signal this way is called AC coupling, because only high frequency signals can pass through the capacitor. The capacitor will have infinite impedance for DC signals, acting like an open circuit, and low impedance for high frequency signals, acting like a short. We can see the effect of AC coupling in our large and small signal versions of the circuit. The large signal circuit on top excludes the AC coupled branches because the capacitors are open circuits at DC. On the other hand, the small signal circuit on the bottom shorts the capacitors and the large signal voltage sources, for instance VBB down here, which results in RB falling in parallel with RPi and RC falling in parallel with RL. This collector resistance in parallel with the load resistance sometimes bothers students when they're first getting used to small signal models, but I find the circuit less strange if I remember that the small signal circuit is only representing changes from the large signal circuit. So these two resistors being in parallel is a way of thinking about how much the node voltage will move when current passes through it, or is pulled out of it. The derivation of the large signal bias point is the same as we've seen before. The base voltage is VBE on, the base current is set by the voltage across RB, and the collector current is set by beta times IB. We're going to take a more careful look at the small signal circuit, and we're going to start by finding VB, which controls the current in the dependent source because the emitter is grounded. So if we know VB, then we know VBE by proxy because the emitter voltage is 0. VB is just given by a divider between the source resistance and RB and RPi in parallel. The collector voltage is the voltage attached to the load, so it's the output of our circuit. That means our ultimate goal is to find a relationship between our input Vin and our output Vc. We write KCL at this node to start that process, which I've done over here. And immediately something looks a little bit weird. If we follow our instincts, it looks like all of the currents should be leaving the node, right? If we have a positive Vc, current will flow down RO, RC, and RL, and the dependent source insists that current flows down it if VBE is positive. So we'd expect current to flow this way in all of the branches. However, that leads to a KCL equation with 0 on one side and a bunch of terms on the other. And if we combine our resistors in parallel, it becomes really apparent that either the dependent current source current needs to be negative, needs to be flowing upwards, or the resistor current needs to be negative and flowing upwards. Equivalently, that means that if the base voltage moves up, we expect the collector voltage to move down, because there's going to be a negative coefficient relating them. We can find that coefficient by rearranging this equation a little bit. And we see that Vc is equal to some big coefficient times Vin. We refer to this coefficient as a gain. You may note that the gain is a conductance times a resistance times a dimensionless resistance ratio. So overall it has no units. That makes sense because this gain turns a voltage into a voltage. You might also note that the gain could be bigger than 1, because only one of these terms, this divider, is guaranteed to be smaller than 1. These two can assume any value, sort of in theory. In practice, in this class, the parallel resistance will usually be a few kiloohms, and GM will usually be a few millisiemens, which gives us a gain that ranges from 10 to 200. Finally, you might note that this gain is negative, which speaks to the strangeness that I was pointing out with currents flowing upward out of ground in these resistors. This indicates that a small increase in base voltage will result in a small decrease in collector voltage relative to the bias point. However, this makes sense because the total signal VC is actually the same as this large signal expression. It's equal to VCC minus total signal IC times RC. And the total signal IC increases when VBE increases. So we expect our total signal to go down as our base voltage goes up because IC gets bigger. That's reflected in our small signal model because we are adding a negative value to our large signal bias point. So our total signal is going to be smaller than the bias point when the base voltage is increased. So in summary, transistors can be used to create a small signal voltage gain, which we saw in the final expression on the last slide. This amplifier is called a common emitter because the emitter is grounded. The collector voltage in a common emitter moves opposite the base voltage, which results in a negative gain, and it has this weird effect of making current flow up from ground through a couple of resistors in the small signal model. But that negative current flow and negative voltage shift, or negative voltage gain, makes sense when you superimpose the small signals onto the large signal circuit, because the total signal collector voltage is equal to VCC minus ICRC.